Hello and welcome to IEEE Soft Robotics Podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Agogino, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks.
Hello and welcome to IEEE Soft Robotics Podcast. Hello, Alice. Thanks so much for joining us in the podcast. I would like to ask you how you would like to define yourself for the audience who first time listening to you.
Well, my name is Alice Agogino, and that was an unexpected question. I define myself along multiple dimensions. I love everything that I do, but I don't work just in robotics. I work in product design. I work in humanitarian disaster response and recovery. I work on a wide range of projects to alleviate poverty, for example. And I love hiking, and I love my family and doing things together. I love traveling and visiting the world, and I love learning new things and meeting new people.
Wonderful, wonderful. And how was your childhood, Lewis? Do you remember how was your childhood? Yeah, being just yeah.
I had an unusual childhood, but I didn't realize it at the time. My mother was a physics professor, and she defended her dissertation when she was pregnant with me. And my father was an anthropologist. So in one sense, I had reverse role models. My mother was very analytical and scientific, and my father was very emotional and socially sensitive. But they were both excellent in their own fields. And so my father is an anthropologist, archaeologist, went all over the world, and he was Indiana Jones, basically. And so I went with him quite a bit. And then I would go to my mother at scientific meetings, and I didn't realize how rich I was in the life that I led. But my parents put all of their money into their work and not into clothes or anything else. And so all my friends called me the little match girl because I always had holes in my clothes. And I didn't realize that even though I probably had more money than them and more privilege than them, I looked very poor, which helped me become humble, actually, to understand and work with people from all walks of life, because I appreciate the strength and the value and the richness that people have that's not measured by money.
That's so wonderful. Yeah, very interesting to hear this story. Yeah. So maybe I'm curious to ask you, Alice, because you really did a lot of achievement in the field as a woman in the field as well, and now you're leading squash robotics as well. But if you can tell us about your interest, how you developed your interest in robotics field and figure out this is what I have to do, like a research line robotics, and how you would define also robotics as well.
So I've always been interested in technology and robotics and what it can do to help the human condition. What interested me about robotics was not that human-like, the anthropomorphic robotics, the ones that look like humans, but robotics that worked with human beings to improve the human condition. So I was interested in human-robotic interaction. I was interested in human-computer interaction, but the role that human robotics could play in the teamwork. And my interest in squishy robotics or soft robotics was that hard robotics are hard to be friends with. It's hard to feel safe around some large robots that could fall on you and hurt you. And so I was very interested in soft robotics for that reason.
So how you would like to define soft robotics in that case, from squishy robotics perspective?
Well, when we started the company Squishy Robotics started from my research from NASA. I had a grant from NASA to conduct scientific missions in which we develop a probe that had scientific sensors inside the probe, delicate sensors that it could either land on the surface of a planet or be shot from a secondary rover, survive the impact and walk away and do scientific monitoring. And we picked the robot, the design, that was compliant so that it could keep the sensors safe within a compliant structure. So soft robotics is a broader field, but our area of soft robotics is with compliant robotics. We started the company Squishy Robotics when we were looking for earthly applications of our technology. And we played around with different titles. At first, we called ourselves Tensegrity robots, and nobody knew what a Tensegrity was. We called ourselves soft robotics. People got it very confused because they thought of squishy teddy bear robots. And we went to squishy robotics because that's actually what our robots are. They're compliant. You can squish them, you can hold them, you can squish them flat.
Yeah, yeah. I'd like to stop in Tensegrity because I think it's very interesting when I see for origami or in Tensegrity and how these structures is combined to make this kind of, the squashy shape. Or if you can tell us about the science behind Tensegrity for people listening, first time listening, and how you can incorporate material science in these structures and how you design them in a certain way.
So the term tensegrity was coined by Buckminster Fuller, who is a famous architect and inventor. And it's a combination of two words, tensile integrity. And what it means is all the components are either in tension or they're in compression. Either they're hard rods or they're elastomers and have some kind of ability to stretch. And so there are many different tensegrity structures that you could define for a robot. We chose to have the 6-bar robot because that is the smallest robot, the least complex, yet it has all the dimensions of a tensegrity robot. It has 6 compressive elements and 24 elastomer elements.
Yeah.
The reason it is compliant is because it has so many elastic elements, and no two compressive elements touch each other. So you have no bending forces. All you have is a sensor network. And so if one side of the robot gets hit by something very hard, like landing on the ground, immediately the tension gets shared among all of the elastomers within the robot. And so it dissipates any force concentration.
Yeah, yeah. I think this is really interesting concept, especially when we see the landing of or Mars, for example. I think that's a very interesting example that you really shared, and still we see many examples for Tensegrity, all sorts of robotics. But if you can tell us about what could be really challenging in designing them in a certain way for energy consumption, for example, what you're looking for in designing the structures, what's something you can avoid like a trade-off in the design process?
Well, there's always a trade-off in weight. So when we drop a squishy robot, the versions that we designed to drop, you'd like it to achieve terminal velocity before it hits the ground, because that means if it's light enough to do that, it means that you can drop 10,000 feet or 1,000 feet. It makes no difference. We have been dropped 1,000 feet by fixed-wing aircraft that survived. Many times dropped by drones and helicopters. But you do have to keep the weight light, which means you can't carry a heavy payload. So there's always a trade-off there. If we were to carry a heavier payload, we'd have to have a bigger structure. So that's a natural trade-off that we have in the system there.
Yeah, yeah. And for example, in environment, the interaction with the environment, how it looks like when we go to something beyond the Earth, because that's example what you're really trying to do or already did it before. So what could be the element in design process in terms of selection material? And when we see also the last few days about how we have designed the helicopter very lightweight and how the comparison between the circumstances on Earth different from other planets. So if you can tell us about the design consideration in that case for the environment interaction.
Well, that's an interesting question. It turns out that we tested at moon rover sites at NASA Ames. And the environments that you would face, say, on the moon, like going down craters or tunnels or going up slopes, are very similar to Earth. Gravity is, of course, different, but some of the terrain actually is very similar. And so we would create structures that move by shapeshifting. We change the length of the elastomers, and that changes the center of gravity. And there's kind of a zigzag motion as we change the center of gravity to go forward or to go right or left or go up slopes. And with that change, it does mean that we can walk, But it also means that if we're going between rocks, we can become smaller, taller, and less wide. So it provides a lot of opportunities. But because there are so many variables for control, the control space is quite big. It's very hard and it's not intuitive to figure out what we would want to do to achieve each of those states and each of those notions. So we started out using artificial intelligence and various genetic algorithms to come up with feasible solutions and then optimize the solutions. And right now we're going to compiling those solutions that we have that work effectively into a set of gates that we would put in lookup tables so it could be used in real time, which we have done, but we're trying to improve the energy efficiency of those right now. So the idea is we could pull on all 24 cables, or we could pull on 2 or 3. The fewer cables we pull on, the less energy is required. But on the other hand, it makes us slower and we can't achieve all the motions that we want. So those are some of the trade-offs, and we're looking at what, say, a first responder, somebody using our product, would want to do with it to decide which is the optimal set of gates that we would want to pre-program into the system.
That's just so interesting. But I would like to go back again about the structures, because when we see that the structures, sometimes if we have nonlinear structures, and that's something discussed a lot in the podcast, and it's not a new idea how we can couple the geometric nonlinearities and also material nonlinearities. When we go to something, as example, Mars, for example, different environment, how do you see the material nonlinearities? Could you think that this is something I can use, or just to play, or only in the structure, using Tensegrity or nonlinear geometry structure? How do you see the coupling or the material selection with the nonlinear structures?
Well, an interesting question. I mean, we use all the tools that are at our disposal. So we come up with different simulation environments. Some of them are dynamic environments. Some of them are very much materials-oriented environments. But we also test everything out in hardware in many different ways. And so I think we always have to validate our software, but I think there's a certain intuition as designers that we have by testing and working in hardware and experimenting many times. And so we have dynamic types of calculations help us in dynamic motion, but don't necessarily help us with material properties. So we've had to have several programs to simulate the environment, but then test them out in real time. And our staff loves testing in real time. It's just so much fun to drop a robot from a helicopter. It's just so much fun to drop it from a building. And so we love testing as well, you know, on slopes, outside, in woody areas, and that validates some of the software that we work on. So with nonlinearity, you don't necessarily have a clear, you lose some of the intuition of how the system works, however. And that's why I think human beings who are working on the design of these tensegrity systems have to work with them both in simulation and hardware to develop it.
So do you think simulation now, if we, because like when we saw the example of testing, do you think simulation so far, how much do you think we have to capture the real dynamics or the changing behavior of the environment? How we can enhance that, how we can design simulation that could be efficient enough? If you can pinpoint example for that, how we can reach this level to reduce the cost of experimentation, and if that's something you think is really worth to be considered.
Well, you know, modeling is an interesting design problem in itself. No model is perfect. And so do you want a quantum model or do you want a Newtonian model? What is the model that's right for you? And rather than have one big mega model, we have a bunch of separate models for different purposes. That is as accurate as they need to be for the information that we want to get out of it, but not a lot more, because some of these models can be very time consuming to run.
Yeah, I agree with you. That's a good point. So if you can tell us about what could be something you think is very promising in terms of designing the structure of the soft robot. Example, where we have squish robot now, but what do you think maybe other examples we still maybe we didn't give much attention as a community in soft robotics? What's something you think still missing and we don't give much attention to it at the moment.
Well, I do think the human robotic interaction is getting more attention than it used to get, but I think it's critical with human beings working with robots. It used to be the robots were designed and then humans learned how to program and work with the robots. But my philosophy, and I think the direction we need to go, is more designed together with the human robotic interaction with the design of the robot. For instance, with Tensegrity robots, we're talking to first responders. We've talked to over 250 potential customers to understand their needs and what they need for better situation awareness. And we're looking at how can a first responder control the robot that might be walking in front of them or beside them to collect data, or send them out to a hazardous environment, say a hazardous material spill in front of them so that the robot goes in the hot zone while they stay in the safe zone. And so we're working at different human robotic interactions like hand gestures or just holding the robot the way they would move the robot in their hand to designate the direction they want the robot to go. That's intriguing. It makes the problem much more complex when the design of the hardware of the robot is somehow coupled with the cognitive capabilities and preferences of the user. But I find that challenging and exciting area to work in.
So maybe I'm curious to ask you, Alice, about what could be something challenging about the designing using techniques like Tensegrity. What's something still challenging for you, or technological roadblocks you think we still face? I think that now, as you highlighted in the space for application, for example, we see success here, but what's something you still see we need more advancement here or development, or still so challenging in designing?
There are lots of them. There's so many. We have a long list of challenges we're working on. We are trying to prioritize those based on
if you can tell us, what could be challenging.
But they're intriguing things. We have a product roadmap of where we want to go, for example. We started out with, first, we just want to be able to drop from a big distance and get in there and sense. Next, we want to walk around and walk in rough environments. And that is challenging, and depending on how high a slope that you want to walk in and what kind of terrains you want to walk in. But what if you need to climb upstairs or hop over a fence? Well, that becomes yet another challenge that we don't have the technology to do right now, but we're working on it. We're working with Mark Muller, who's a drone expert at UC Berkeley, on a joint project in which we're putting rotors on the compressive rods. And so those rotors would allow us enough hopping motion or to bang against walls to climb up small stairs or go over a fence. Hear from many of our customers that are in flood-prone areas that they want a floating robot or a swimming robot. Well, that's another challenge that we've got on our product roadmap that we would like to solve in the future.
That's great, So coming back to scenario for interacting with the environment, do you think about how we can design them in a redundant way? For example, if damage happening for certain parts, do you think the structure will lose its functionality? How you imagine a scenario like that about the damages they can face with the environment? They still can function?
Yeah, that's an excellent question. And that's what NASA asked us a lot. The idea of a tensegrity network is that you need everything to be in tension. If you lose that tension and you have an elastomer that isn't tight, then you're in danger of losing control of the robot. So you can lose one, maybe two, and have some motions. But if we lose all of them, clearly we can't. And so there's always a trade-off there. The advantage is that unlike many robots, we can make multiple robots because they're relatively inexpensive compared to most robots we produce. And so there is an advantage in releasing a fleet of the robots rather than relying on one.
That's very interesting. So I'm curious about the scenario. Do you have something in your mind for design or modeling? You saw that would work out, but when you're designing in real experimentation, you found surprising result or something you didn't expect it was counterintuitive to what you designed, maybe yeah, in modeling, or do you have any kind of scenario happen like that? Unexpected result?
Well, we are noticing some non-dimensional parameters that we hadn't experienced when we're scaling up. We worked on a project where we started with a regular size robot and moved up to larger robots to carry heavier loads. And we're finding some non-dimensional parameters that are coming out of the best design from each of those. So that was exciting to us. We don't understand from first principles why that would be the case, and we don't want to release it now because it's proprietary for the company. But it's exciting because it means we can scale almost anywhere,
Mm-hmm.
a wide range of applications. So we're excited about that.
Interesting. Yeah.
But a lot of the design,
Mm-hmm. Mm-hmm.
what does the foot look like? The landing, at the end of each of the rods, we have feet, basically. They're just little rubber containers for the ends of the rods. But whenever we do that, it took a lot of detail. We simulated, how soft they would be, how much of an impact they could take, and then we tested. I think we tested 50 robots
Mm-hmm.
during the
Yeah.
time we were working on this. And so sometimes the devil is in the little details to have, what is an appropriate component that goes into the bigger system.
Yeah. Yeah. Yeah.
Be tedious, but it's
Yeah, it's very interesting. I think what you said about the landing, because I think that's something I'm curious to ask you. Do you think when you design structures, do you have using multi-materials in that case, or are you depending on the structure or intelligence in that case? How far it's intelligent when you design them to achieve certain behavior? If it's to go to landing, for example, on Mars, for example, how do you see that? Do you have to play with multiple material in the same structure, or just using the intelligence of the structure? How it looks like with the landing example frame to Stefan and me, last week.
Well, that's a very rich question, and it depends on what you mean by intelligence.
Mm,
But let me answer one possibility of intelligence,
mm,
and that is feedback control and machine learning. So some of our robots were designed with reinforcement learning in mind, so that we improve the gates and we improve not only the design, but we also improve the controls using machine algorithms. And that requires, for instance, the work that we did on the moon, that you use artificial intelligence over a whole wide range of terrains and backgrounds. And especially backgrounds you've never seen before in your life. Now, the advantage of the moon is that a lot of it has been well mapped out, but a lot of it has not been well mapped out. So I would have limited expectations on what we can do on our machine learning algorithms on the moon surface. They'll apply in some, they'll apply for going downhill in craters, or they'll apply on flat surfaces. But I do think this is why I'm a big fan of extracting out the general principles that come out of these intelligent algorithms into walking gates we can use, so that we're not going back to machine learning for real-time control. That the intelligence comes from understanding and compiling out insights from these algorithms.
mm-hmm, mm-hmm. That's also interesting point.
Here's another way to think about it. You are a tensegrity.
Mm,
Your backbone is in tensegrity. You actually have a spinal column that is in which the compressive materials are only separated by ductile materials. And so over time, evolution has optimized what some of these human beings and other life forms look like. And some of them do have aspects of tensegrity robots. So we are borrowing from the intelligence of evolution.
mm-hmm,
There's a robustness in the structures and the algorithms that we're working
mm-hmm. That's interesting. Yeah. And what could be other maybe crazy design ideas you have to test, for example, because we know that when we look to nature, we don't have this optimum solution, it's just result of evolution. So I don't know how you see that designing new structures or crazy structure. I don't know. Of course, you have to look for certain expectations. But do you have any ideas beyond Tensegrity?
Well, I'm living and breathing tensegrity right now.
Okay.
But I do a lot of work in disaster response more broadly,
Mm-hmm.
also poverty alleviation. And I'm a firm believer in resilient structures because after any hurricane, earthquake, or some other natural disaster, people get poorer and poorer.
Mm.
And so these natural disasters are hurting the bottom of the income pyramid more harshly than everyone else. And so resiliency to disaster is something that I care about and I think is a critical problem. And you can think of it as resiliency when you design the buildings initially. You can think of it as resiliency into the service or the infrastructure, whether it's telecommunications or roads. I think no matter what we do, that kind of resiliency that we see in a tensegrity robot just inspires me more broadly in terms of
Mm.
resiliency to unexpected interactions with the planet.
That's wonderful. Yeah. So maybe I'm curious to ask you what could be that you think very challenging when we design soft robots. For example, the squishy robots that we see that there's not much companies in robotics in general. So why do you think it is so challenging to have a hardware company when it comes to robotics? And what are factors to make it successful?
Well, I think the major challenge for any hardware company
Mm-hmm.
is current investment infrastructure favors software because the profit, once you have a successful solution, the profit margin can be quite great. Whereas in hardware, there are many aspects of the supply chain, what you're purchasing, the decisions you make, de-risking the hardware, and it doesn't lead itself to the kind of scale of growth that software can acquire when you're working with investors. And so it is much more challenging to work in a hardware company. But we actually consider ourselves an information company. We provide life-saving, cost-saving information in real time through rapidly deployable robots. So the robots are just a vehicle to give information. And we're excited about what we can do with the data analytics and machine learning over time to improve our ability to identify failures before they occur, prognostics and diagnostics overall, and to help in prioritizing the workflow in a disaster situation when you're brought in, because so many things happen at once. What does a first responder go to first? What does a maintenance crew go to first? And so I'm excited about growing our data analytics over time, but I think it's important that we are a combined software and hardware company.
Yeah. Yeah. Wonderful. Yeah. So maybe if the student would like to ask you, curious about designing structure and when it comes to integrity, what could be the biggest step or maybe the initial steps you have to do to understand integrity for any student listening to you? What do you recommend? How we can start?
Integrities, I'd say just build one.
Build one.
Be creative and build different ones in different structures and learn from that.
Mm.
I mean, there are tensegrity concepts that a plane could be a tensegrity and could transform itself into a ball that drops. But you can have flying states as well as dropping. I think tensegrity lends itself to a kind of creativity in design and imagination that doesn't constrain itself like other structures do. So that's what I always tell students at first working on it. Get your hands on it and build one.
I'm curious to ask you what is maybe the most challenging moments in your career? What could be most challenging moments and you faced it or you proved it?
I think when I started out in anthropology when I was an undergraduate, I was going to do what my father did.
Mm-hmm.
And then I realized as I got into anthropology, it didn't really take advantage of certain strengths that I had, particularly in mathematics. And for whatever reason, I decided to move to mechanical engineering, not realizing at the time there were no women in mechanical engineering when I decided to move. But I worked hard. I just said I was going to finish up my last semester in anthropology and then move over to mechanical engineering. I'm the only person in the world I know who has ever done this, by the way. Someone let me know, because I would love to share the experience. So I moved, I did 2 years in anthropology and then moved to mechanical engineering at another university. And I decided I wanted to graduate. So that meant I had to take first semester calculus and third semester calculus in the first semester. And then the second semester, I had to take second semester calculus and fourth semester in the same semester, and then take all the other courses on top of that. And I went to my advisor and asked him to sign off on my course load for the first semester, which he did. And then I said, I'm looking ahead for the second semester. I'd like you to sign off on that. And he said, I'm not going to bother because you're not going to do the first semester. And I literally cried on the way back to my dorm room. And I lay in bed and I was catatonic. Eventually I think I fell asleep. And I said, I worked so hard for this. I finally decided this is what my career is going to be. And he says, I'm not even going to make one semester in this program. And I woke up in the morning and I said, I'm going to prove him wrong. And that was it.
That's wonderful and powerful as well. Thank you for sharing that. Thank you. And maybe I'm curious about your aspiration. What is your aspiration? I'm really inspired by you. What are you doing? What is your aspiration? You still have aspiration for, maybe for spatial robotics or your academic career. Yeah.
Well, I feel like I've done a lot more than I thought I ever would. My mother said I would never live past 30 because I was quite a risk taker, actually. So I lived past 30. I've achieved that. There's so many more things we can do in this world. I just want the world to be a better place where we live.
Wonderful. Yeah. And what could be the most important quality you have gained in this journey? What is the most important quality you have gained?
Wow. Well, there's a lot, but I think just an appreciation for the inherent talent in everyone. Everyone has something to offer. And stepping back and trying to understand how you can help that person achieve their goals, I think is what I've learned the most from. People that unexpectedly, even students I've learned from and have recognized their potential and inherent ability.
Great. And what could be the most important advice was given to you and was life-changing, maybe personally or professionally?
Oh, that's hard. I think that you have to set your own direction. Too often people ask me for advice and to follow my model, and I said, never follow my model. It's not going to be right for you. And so I think the advice I give is you've got to decide what's important to you, what your own strengths are, what your own goals are, but find a path and find a journey that works for you.
I agree with that. I agree with that. So thanks a lot for also for saying that. So actually, I feel you have a lot, but I think we have to close here. But maybe if you have any final words you would like to say for robotics community, any final words?
I think we need to improve the diversity of the robotics community, the gender diversity and diversity along many dimensions. I think there are great people working in the community, but it'll be an even greater field with more diversity.
Yeah, absolutely. Absolutely. I amplify that as well with you. So thank you again, Alice. I think you're so inspiring woman and also engineer, professor. So thanks for all what you're doing. And it's a pleasure to have you. Such an honor to have you. Thanks a lot.
Well, thanks for the opportunity.